One of the first pages you got today, I've colored it in purple for you so that you know it's important that you should keep it, and we're going to keep coming back to this throughout the course, is probably some stuff you already know. Building regressions with the calculator. So this is the stat edit stuff that you've probably been doing for a while. All of this is really the same. I'm going to make it not even really that different probably from what you know. I'm just going to add a little something at the end during our notes today. So we just take a second to look through the steps to writing a regression on a graphing calculator. Again, this now becomes like a formula chart-ish for you. Step 0 is to turn on the stat diagnostics from the mode menu. So let's make sure we know how to do that. Look at your calculator. And depending on the kind of calculator you have, these instructions might slightly differ. I forgot if the newer ones that are backlit, the CEs are different. But the instructions for the yellow ones are you press mode, and you're going to scroll down until you see stat diagnostics. Typically, and every time you reset your calculator, the stat diagnostics turn off. Why? I don't know. They're very helpful. We're always going to turn them on. We're not actually going to use them today, but I want that to be a part of our habit that we always make sure the stat diagnostics are turned on. If you're going to use the stat button, you turn on the stat diagnostics. Does anybody need help finding that part of their calculator? Mode, and then you have to scroll down. It's off screen technically, so scroll down till the screen's going to move down. It's on like the second page. Bless you. Okay, cool. So you highlight over the word on, you press enter, it will move to on, and then you get out of the mode menu by pressing quit, which is above the mode menu, so press second mode to quit. You should be back at like the regular screen now. So again, if you need a visual of what that looks like, here's mode. This is the newer like calculator, so if you have a CE, that's what I'm showing you. But again, stat diagnostics, you go over to on, you press enter, and then you get out of this. Okay, cool. If you look at the instructions again, it says press stat on the TI-84 and select edit. That's the first button. So we press stat, we press edit, and it takes us to these lists. And oh wow, the text didn't move over like I told it to. That's supposed to say enter the data into the list with L1 being X and L2 being Y. I think we know those instructions already though, so I'm not really that worried. We don't have any data right now, so just follow along with me. After we have the data in there, we would press the stat menu again. How popular today? Okay. Cool. So we would go to stat. We go over to edit. We've already done that part. We go over to calculate, which is the second menu. And this is where you have to make a choice. Now, we don't have a problem. We're working right now. We're just looking through the calculator. But you have all of these choices for the type of regression, REG, that you're wanting to use. You have options for linear. That's option 4. Quadratic, cubic, quartic. This is a second version of a linear regression. This is great for stats if you ever take AP stats. We're actually going to use that one today. Your natural logarithm regression, your exponential regression, and then that's basically all we'll use in this class. You have logistic and sign, which we briefly talk about for a moment. But those are the ones that we're going to mostly use in this class. Let's, for funsies, just to look through it, let's select option 8, which again is a linear regression. Y equals mx plus b, it's just in b plus mx form. Then you get this menu screen. Okay, cool. You've probably never changed the x list and the y list because you really shouldn't. You've typed previously all of the x values into L1 and all of the y values into L2, so we don't need to change this. And for my class, I don't think we ever will change that. But what we will change on this menu is the store regression equation. If you look at your paper, the purple paper I gave to you, what does it have on the picture of that linear regression on the equation line that says store regression equation? What is there? What does it say in the picture? Y1. We want to put a Y1 right there because it will ask your calculator to go ahead and type whatever regression you get into Y1 for you. You don't have to round numbers. You don't have to type numbers. That's great. Does anyone remember how we did a shortcut to get Y1 earlier this year? We did it when we did average rate of change. It's when I confused everybody with the Y1s in the equation. Alpha trace. So we're going to press alpha trace, and it brings up a shortcut menu for all of your y variables. We want to type this into y1 so that it will graph it on our calculator. So we just press enter. Types of y1 right there. Hooray. If you were to right now press calculate, nothing would happen because we didn't actually type in any data. But that's going to be steps you're going to use later on in class when we actually are running some regressions. Does this all look familiar to you? I'm seeing some head nods. Great. Cool. If you flip this paper over that I gave you, you'll see on the back something that talks about residual plots. I am not talking about residual plots today. That's going to be a lesson for future us. I just think that it would be really helpful for it to be attached to this purple paper so that when we do talk about residuals, it's right next to the other steps that we need. So you can politely ignore this for right now, but eventually we will come back to this, which means don't lose this purple piece of paper. Please, I'm not making you extra copies. Don't lose this purple piece of paper. All right, our lesson for today is all about modeling functions and applications. So we just went through all of the steps of how to do this. Now we're actually going to see an example when we would want to write an equation using a regression. Most of the time, like 99.9% of the time, when you're asked to write a regression, it will be on the calculator portion of the test because we can do this by hand, but it's real ugly. So we usually use technology to help us out. Example 1 says, the age in weeks and weights in kilograms of 5 randomly selected babies from a particular pediatrician's office are listed in the table above. A linear regression y equals to a plus bx. Notice that's not y equals mx plus b. It's just moving the slope and the y-intercept. So that's going to be option 8 again, like we just practiced. Can be used to model these data where y is predicted weight of the baby that is x weeks old. Part A says to write the equation of the linear model for this data. Okay, let's go back through these steps. We've already turned on stat diagnostics. You only have to do that once unless you reset your calculator. So on my calculator, what am I pressing? Stat. Okay, great. I pressed it. Now I need to type data into the table. So what do I select? Edit. Okay, great. Let's type that in. All of your independent values, which for us is t, the time in weeks, goes into L1. Your outputs, which is the weight of these babies, goes in L2. I'll give you a second to type all of that in. Okay, fabulous. Thank you for checking on your neighbor for that. So now that we have it all typed in, we actually want to run the regression and find the model for this situation. So we press stat again. This time we go over to calculate because we're trying to calculate something. And it told me a specific version of linear regression to use. Which version is that? 8. So again, the problems are most likely going to tell you which kind they want you to use unless that's part of the problem of identifying what kind to use. A plus bx is this version number 8. So we select number 8. You can scroll down and select enter on 8 or just type 8 and it will work. We have typed our x's into L1s and our y's into L2, so we don't have to change anything. But on a store regression equation, what's the buttons that I press again? Alpha, trace, nice. And then enter. This again is telling the calculator to put or store the regression in Y1, so it will graph it for you. We go down to calculate, we press enter. And it's going to think for a second, and it's going to show you something like this. In AP Calculus, you round to 3 decimals. How polite. They gave us exactly 3 decimals. So we go ahead and write this equation. On our paper, we should write that y is equal to 3.545 plus 0.185x. Now remember that we did this not in y equals mx plus b form. You fill in the exact pattern that the calculator gave you. It says A goes first with no x next to it. B goes second with an x next to it. Follow the patterns. What's nice is the calculator shows you the pattern. If you kind of remember what we use the r squared and the r for, if you've ever taken stats or remember from Algebra 1 correlation coefficient, yes, that's what we're finding, but not today. That's going to have to do with the residuals things that I told us is a problem for future us. But again, we're just setting ourselves up for success here. Okay, cool. So on my notes, I have that written down. Sounds great. Part B, though, goes on to say, using the linear model from Part A, so the equation we just got, what is the predicted weight in kilograms of a baby that is 10 weeks old? My question for you is, if they told us 10 weeks, did they give us an input or an output? Input. So we're going to want to plug that number into the equation, which, yes, 1,000%. You could type 3.545 plus 0.185 times 10 into your calculator, press enter, and get your answer. Or use the hint that's on the side of the page. This will throw it back to when we did average rate of change and I confused everybody. You can quickly find the values of functions that are saved in Y1, which we did, we stored it there, From the home screen on the calculator, typing exactly this into your calculator. It is telling it, like function notation, take the number 10 and plug it into y1. Not multiplied by, but plugged into. So if I do that on my calculator, I just go to the home screen. I use that shortcut again, alpha, trace, enter. And I'm saying, all right, take the function y1 that we stored, and I want you to plug a 10 into it. You type it on your calculator. Make sure you know how to get that y1 to show up. We press enter. Pow, we have our answer. For me, the way I want you to write this down on your paper is function notation, essentially. You're going to say y, oh, let me show you, not the calculator. You're going to say y of 10, because that's what we plugged in, is equal to 5.395, and then this is the weight, so kilograms. Yes, I know it's exactly what the screenshot on your paper is, but I just wanted to make sure we had that. Question so far? Fabulous. Part C says the weight of a sixth baby is 5.3 kilograms. Using the model from Part A, what is the age in weeks of this baby? Now, if they told me a weight, did they tell me an input or an output? Output, which means it is the equal to number. So what I've done now is I said, okay, well, I have this equation, 3.545 plus 0.185x, and I know that's going to be equal to the numbers 5.3 kilograms. That's the output that I'm looking for. We want to know the input, or the x, for this value. You know what I'm just realizing? And I'm going to go back and change something. We shouldn't be using the variable x. What should we be using? A t. Let's go ahead and change that. Consistency is important. Doesn't really change anything, I know, but time. That way we know we're looking for weeks, that this is the time in weeks that the baby has been alive. Okay, well, that's just a simple equation. We've been solving equations like that since Algebra 1 in 8th grade. So we subtract 3.4545, from both sides. 5.3 minus 3.545 is 1.755. We divide by 0.185. We'd get that the time in weeks is 9.486 weeks, which you would say somewhere within 9 weeks old. Questions, comments, concerns about one regression modeling equation? Bless you. Yes?
If we don't put the right variable, would it get like counted wrong?
You know, I don't know the answer to that. Did y'all hear his question? So I will look into that because I actually don't know if putting the wrong variable, AP readers will count that right or wrong. I would assume yes, because you didn't answer the question. It didn't ask for X, it asked for T. So let's try to make sure we always use the right variables, but I don't know yet if they would still accept it. I would assume no, use the right variables, but I'll get back to you. Other questions? Okay, cool. Here's another one. Example 2 says the table provides data for 8 ordered pairs that are x, y. Cool. Which function type best models the data in the table? Linear, quadratic, cubic, or rational? There's many ways we could answer this question, but I want to see what you're thinking first. Look at the outputs from this table and tell me what's the pattern-ish. Doesn't have to be precise, but what's happening with those outputs? They're what?
Increasing.
They're increasing the whole time? You're right, they are increasing. So they're increasing, 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 increasing. Oh, decreasing, decreasing, decreasing. What kind of function increases then decreases? Quadratic. So if you remember, a linear function has data points that are going to just go one direction, either all the way up or all the way down. Quadratic will have some sort of parabolic shape, either down then up or up then down. Cubic kind of looks like a stretched out S, but it will always be either totally increasing or totally decreasing. And rational is the ones that has the weird decreasing big jump but still decreasing section, or vice versa. If you did not recognize right away from the table what is happening with the data points, or you're not sure between some of the answer choices, there is a different something that we can do with our calculators to visually see what's happening with this data. Let's go back to our stat edit menu and let's go ahead and type in these coordinate points. Now, here's some shortcut tricks of the trade with stat edit. Number one, you don't have to delete stuff. If you just start typing over it, it types over it. So if I were, look how my cursor is over the 4 from the previous problem we did. If I just press 0 and press enter, it changes it to 0. So don't do the deleting stuff. That's how you accidentally delete lists and it freaks people out. But if you do like completely clearing things at first, everybody look up at the screen for a second. Don't press delete when you're up here. It will delete the list. You want to clear the list. If you press clear and then enter, it clears the whole list. So if that bothers you to have to go overwrite it, you just want it to look plain and neat every time, don't press delete, you press clear. Really, on this entire menu, never press delete. That's how you accidentally get rid of lists. I'll give you a second to type in that data, please. If you happen to accidentally delete the list, the easiest way to get it back is to reset your calculator. 2nd plus 712. There's another way, but that's the easiest way. Just reset it, start again. Okay, fabulous. So we have it all typed in, hooray. Now, what should be pretty easy to visually see what kind of data we have is to see it in the graph. If I press graph right now, it still has my equation from the last problem in here. So that's not what I want to see. I actually want to see the statistics we just put in there. You're actually going to go up here above y equals is the words stat plot. Have you ever pressed that menu before? Maybe, maybe not. You're going to press second and y equals. It's going to bring you to your stat plots. You just typed a whole bunch of stuff into L1 and L2. So you're going to open the first stat plot by pressing enter. And you're going to turn it on. It's off right now, so you turn it on. You double check real quick that the X list and the Y list are coming from L1 and L2 because eventually we will change that, just not today. Mine is the CE, so it has some more options. Yours won't ask for color because it's in black and white, so sorry. But then you're going to go back to your graph. Now again, I still have the equation from the last problem we did in here, but I also have these like points that have shown up. Interesting. Here's what I want you to do. 2 things. Number 1, I'm getting annoyed by this linear equation being here from the last problem, so I'm going to go delete it. I go to y equals, goodbye, and I just press clear. It's cleared. Okay, second thing I'm going to do is zoom the graph so that I accurately see the data. You could use the window for this, the way we've been doing. Or you press zoom and you use option 9. What does option 9 say? Zoom stat. Write that down for yourself. It's not written on your notes anywhere, but write down zoom 9 zoom stat. Especially if you're not sure what kind of data this is going to be and you want to see it. Okay, you're going to want to press option number 9, which is zoom stat. When you press 9, your calculator is going to go ahead and zoom for you on a screen that's great. This is like the little magnifying glass on Desmos that like takes you to your data. Zoom 9 does that. This kind of confirms our suspicions that this is a what kind of function? Quadratic. Look, it goes up, it comes down. That's a parabola, it's quadratic. So if you're not sure what's happening with your data by the y values, which some of us did notice, you can always double check yourself by typing in the data. You'd need to type it in anyways to run a regression, so it doesn't really hurt to do that early. So to answer our question, we're going to say the type of function type that best models the data in the table is quadratic. And just because we want to make sure our notes are nice, we're going to tell ourselves why. It looks like this. There's my explanation for myself. When I graphed it, the outputs go up then down or down then up. That means it's quadratic. Part B goes on to ask you to actually write the regression model for the data in the table. I want to see if we can finish this out on our own. You've already typed in the data, so it shouldn't be that much more stepwise to get the regression equation, but I'm going to let you think. Okay, if I was working through this problem, again, I already have the data in there, so at this point, I don't have to type it in again. I just go to calculate. Which option am I choosing this time? Quadratic, number 5. So again, you can scroll to 5, press enter, or just press the number 5. Pow. Okay, cool. Don't change the x1 and y1 because that's where, or the L1 and L2, sorry, because that's where we actually want it to get the information from. But we do want it to store in y1. And then we press calculate. So we should write a quadratic that looks like this. It should say y equal to negative 4.883x squared plus 15.958x plus 4.996. We're rounding to 3 decimals. I just realized you can't see me writing because the calculator's still on the screen. Cool, great, awesome. Now that question required us to figure out what kind of data I was presenting you with. This next problem is going to give you the type of data, mostly because we haven't really studied this yet. It's our next upcoming unit. It says the table above provides data for 7 ordered pairs x, y. Using a logarithmic regression, construct a natural logarithm function model for f for y as a function of x. Wow, those are a whole lot of words that I just stumbled over. Write an expression for f of x in the form f of x equal to a plus b times natural log of x, where a and b are constants. It's trying to help you realize what kind of regression we're running. 2 hints here. Number 1 is it tells you the form of the equation, which again, right now you don't really know. I haven't taught that to you yet, although you might remember from Algebra 2. But it also gives you the words logarithmic regression or natural logarithmic function. That's going to be our hint to pick the correct type of regression. So from start to finish, this one is yours. You start by typing in that data. You go run the regression with the correct kind, and I want to see if we can pick the correct kind without me saying much more. I'll give you a few minutes. Okay, so I hear us slowing down, so either we got it or we're lost. I'm at the point where I've typed in my data, and I checked for typos, because I definitely typed one wrong when I was typing this in. I go to stat, I go to calculate, but now I need to figure out what I'm calculating. The problem said natural logarithm. Which option do I use for a logarithm? I think I heard somebody say it. Which one? Number 9. If you're like, what? That says ln instead of natural logarithm. We do write the logarithm part first. It comes from, I forgot what language, putting the adjective second instead of first. But that is the natural logarithm regression, option number 9. So if that's where you got stuck, write that down. Natural logarithm is option number 9. Again, we don't really know what this is yet because I haven't taught it to you, but we go down still with the same steps. We store the regression equation. What is the buttons I press for this? Alpha trace, enter, good. We're going to need that alpha trace, enter. And then we calculate. Pow. So my equation, when I write these down, remember I'm rounding to 3 decimals, should be in the form f of x equal a, my calculator tells me a is 2.864, plus b, my calculator tells me is 1.818, times the natural logarithm of x. The parentheses around the x right now are kind of unnecessary, but it's just a habit for me to always put parentheses around that for a natural log. Okay, again, if you wanted to write that down for yourself, this would be option 9 where it says natural logarithm regression. Questions, comments, concerns? Okay, so one of the things I only really asked you to do once on this paper, but is kind of important for this class, is identifying the type of data correctly. So kind of like example 2, letter A. We're going to just do a quick check to make sure we're pretty good at that because we've been exposed to these types of functions before. So before you flip your paper over, go ahead and get your computers out. We're going to do a quick Kahoot. All right, so thank you for playing that Kahoot. We're going to talk a little bit about modeling with piecewise functions. Now, we've done a little bit of intro with piecewise functions here or there. This is the first time I'm really talking about them within the notes. First thing, though, there's a huge typo on here that I didn't realize till I had finished copying all these papers, and I'm not wasting the trees to fix it right now. I need everybody to fix it, though. On here, I need you to change this to the opposite symbol. So for me, I'm gonna white it out because I am using digital things. This needs to be switched the other direction. That's so embarrassing to me because this is so important that it's facing the other direction, and then I messed it up. Okay, please change that. So sorry. I'll tell you why in a little bit, but before we get started, we're just gonna fix that. Did we all fix it? Okay, great, my bad. Oops. Okay, so a piecewise function. I like to call these our Frankenstein graphs because what's happening is we are taking multiple different types of functions across the domain of the graph and using them at different points. Meaning, when x is less than 1, it's a linear, and when x is equal to or greater than 1, it's quadratic. We're taking two different types of functions and shoving them together for one function. Now, for it to be a function, that means x's cannot repeat, which is why switching that symbol was so important for me. The x value still cannot repeat because it is still a function like the old function rules we've always used. But once we hit a certain x value, we switch to a different function. Okay? The textbook definition says a piecewise defined function consists of a set of functions defined over non-overlapping, no repeat, domains, intervals, and is useful for modeling a data set or contextual scenario that demonstrates different characteristics over different intervals. Frankenstein. You've got this one function happening here and another function happening here across the domain. Is there crickets? Is that what I'm hearing? Did that just start? Ugh, not again. Okay, so what it will look like, a piecewise function will be one function. This one's called h of x, but it will be, again, made up by multiple other types of functions. Our top function here is going to be named f of x. F of x is only in effect when, or given, x is less than or equal to some value a. So when x is less than 0, it's f of x. When x is greater than 0, it's going to be something else. That something else is whatever is listed underneath it. This function takes over once we switch domains. Once we get to a certain x value, it changes to a different function. But it is one function. Function just means the x's do not repeat, and there are inputs and outputs tied together by rules. Here's our rule. Now, the first example we see here, example 4, you've actually done a little bit before. We talked about it with end behavior and some other things. We're just going to make sure we understand when to use which part of the function. So example 4 says for f of x, we're going to have two functions. Again, when x is less than 0, we have this function that's a quadratic. That's for all types when x is less than 0. But the moment we use an input value that is equal to or greater than 0, we're going to switch and we're going to use this linear function instead. It's still a function because my x's do not repeat. We're not overlapping at 0. One of them would be an open hole, one of them would be a closed hole. So the first problem I'm asking for you to do here is f of negative 5. That's just saying take the number negative 5 and plug it into the function. Am I going to plug it into the top function or the bottom function? Why the top? Yeah, isn't 5 less than 0? Which means when I'm using negative 5, this function is in charge. So I'm going to plug negative 5 into that top function looking like this. Negative 5 squared plus 1. Okay, well, negative 5 squared is 25. 25 plus 1 is 26. For the next problem, it says f of 0. For f of 0, am I going to use the top function or the bottom function? Ooh, why the bottom? Because they both have 0 on them. It's the equal to part. Nice. So we're going to use the bottom function and just do 0 minus 1. Well, 0 minus 1 is negative 1. Again, you're just looking for where that input value belongs based on the domains for each separate part of the piecewise function. How about f of 4? Do I plug that into the top or the bottom function? Bottom. So we're just going to do 4 minus 1. Easy peasy. That's 3. Make sense? So you look for the appropriate domain for that input and then just plug it in. Easy peasy. The other thing we're going to do with piecewise functions is write or model piecewise functions using equations. So if we look at example 5, we are going to write the f of x with that big little squiggly line so that we have the different pieces put together. My question for you before we start this is, how many different pieces of this function are there? 3. You have this first part. We have this second part. And we have a third part. That first part that I highlighted in red, what kind of function is it? I get why you said that, but it's even more specific than linear. It starts with a C. Constant. Flat lines are constants. Yes, I get it. It's a line. It's a line with a slope of 0, but they're special, so they're called constants. What's the blue part called? Linear. Is it going to have a positive or negative slope? Great. The green part, what is that called? Linear. And is it going to have a positive or negative slope? Okay, cool. Those are nice questions to ask yourself just to make sure you're on the right track. But if we want to write this piecewise function, I need to make sure I have 3 parts in my function. So I'm going to make that little squiggly bracket really big because I need to write 3 different functions on there. That first function is a constant. What is the constant value? How high is that flat line? 2. So my function is just the number 2, no x's because it's constant. Now between what x values is that red part occurring? Between -3 and -1. Now a couple questions for you. Why did I include the line underneath the less than signs? The endpoints are closed, yeah? Okay, great. Thank you for noticing that. For the blue part, we already said it's a negative slope. What is the slope of that line? -1. What's the y-intercept? Oh, the y-intercept. 1. So my equation is -x plus 1. That's just writing a little linear equation. Between which x values does that occur? Now here's the problem. You answered the question appropriately earlier, that because there are closed dots right here, we use the closed symbol. If I were to do this, that would be wrong. Why? Because it's overlapping. We need one function to be in charge at every point. Otherwise, we have a repeated x value. Yes, I know it's the same, but out of habit, we're just going to pick one of those to be exactly equal to. They're the same value themselves, so it really doesn't matter because you would evaluate it the same. I'm just going to let the red one be the one equal to. We don't really have other information to prove us otherwise right now. So we're just going to let the red one be equal to and the blue one just be less than. But we'll go ahead and make this symbol less than or equal to because of the closed dot at the end. Now the third part, what is the slope of that linear equation? 1. And what would be the y-intercept if we could see it? -3. Here's how we figure that out if you're like, where'd they get that number from? If I just continue this pattern, it would cross the y-axis at -3. That's what we did. Continue the slope of rise 1, run 1. Now, what are the x values where that is in control? 2 to 4. Obviously, at the 4, we have a closed symbol. But at the 2, which symbol should I use? The open symbol, because we already controlled the closed part with the blue. Again, that was my opinion on this question, because we don't have information about which one's in control. But there are, for sure, right or wrong answers for that question on the next problem we're going to do. And you'll see why in a second. Before I do that one, though, are there questions on this? Do we see how each part is controlled by something else to create one function with no repeating x's? Okay, cool. Let's look at part B. How many parts of this function are there? 4. Thank you for saying 4. Let's identify them. We have this part. What kind of function is that called? Constant. We have this part. What's that called? Constant. Whoa, then we have just one random dot by itself. That's important. That coordinate point, that's important. And then we have this part down here. So we have 4 different pieces of this piecewise function. There's still no repeating x's, so it is a function. X's and y's tied together by some rule. Let's figure out what that rule is. All right. Constants are usually pretty easy to write because they're just numbers. So what is the constant value for the red part? -2. Now, what x values is -2 in control of the function? From what to what? to what? 1. Okay, cool. Now I need to choose the correct symbols for this inequality. At -3, I see a closed dot, so I use the closed symbol. But what do I actually see at 1 this time? Open. So I make sure that that is open. There's no opinions on this one. That one's open. Okay. The blue part, what's the constant value there? 1. And when is that in control? From 1 to 3. Now tell me about the symbols I use here. Do I use the closed symbol or the open symbol? Closed for both of them because I have closed dots at the end of the blue. Before we move on, I want to just take a second again to emphasize why it's so important that the red one is not equal to and the blue one is. Obviously, because of the open circle and the closed circle. But if this were closed, would this equation, would this relationship pass the vertical line test? No, at that point we'd have 2 closed dots on top of each other and it would not pass the vertical line test, so it would no longer be a function. You have to make sure we're writing functions, no repeating x's. Okay, for the green dot that I put up there, what is that y value? 3. And what's the x value where that occurs? 4. So you just say this is only in control when x is exactly equal to 4. Yes, I know there's a gap between 3 or 4, but in my graph itself, there's a gap between 3 or 4 where nothing happens, so that's okay. Now, what's the constant value for the purple part? -1, and when is that in control? From 4 to 6. Why did I just write negative? I don't know. From 4 to 6, tell me about the symbols. Open, then closed. Very good. So we take this Frankenstein-looking graph and we just write the rules for each part and tell you when that rule is in charge. That's essentially what we're doing. Questions, comments, concerns? Okay. Then we get this word problem. Hint, hint, wink, wink. I would super make sure we pay attention to this problem for our test that's coming up this week. It says, starting at time equal to 0 minutes, a copy machine makes copies at a constant rate of 80 pages per minute. 1 minute after the first copy machine begins making copies, a second copy machine makes copies at a constant rate of 80 copies per minute, so that both machines are simultaneously creating copies. Both copy machines continue to make copies at their respective constant rates until t is equal to 3 minutes. Let C represent the total number of copies made by the 2 copy machines after t minutes and write a piecewise function that models the function C. Whoa! Here's why we need a piecewise function for this. So we start making copies. How many machines are working at first? 1. So we have one particular rate where it's working. We're working at 80 pages per minute. It's spitting out copies. And then after 2 minutes, another copy machine joins. So what has happened to my rate? It's increased. My function has changed at a different time. That's my input values. So we have 2 separate equations controlling the output of copies at any particular time, so we need a piecewise function. Follow along with me. We're going to start, this one's going to be called C of t. C for copies, T for time. That's the variables it gave me, so I need to abide by the variables it gave me. And we have 2 separate times that are going to happen, so I need 2 separate equations. Here's what I see. First, it says starting at time 0. That's not a highlighter. We have a copier going at a constant rate of 80 pages per minute. Per is telling me a slope, so I know that that's a rate. I know that that is a slope. What is the equation that would tell me how many copies have been printed, if that is rate of change? 80 times t. Okay, great. So we have 80t. Now, when is that function in control? Oh, sorry. Starting at what time? 0. And ending at what time? Oh, it's not 3. 1. That first copier is only working by itself, by this function, until minute 1. Why did I choose to not put the underline underneath there, do you think? Yeah, exactly at 1 it says the other copier starts. So exactly at 1 we switch to the other function. Okay, cool. Let's write the other function. It says 1 minute, blah, blah, blah. Copy machine is moving at a constant rate of 80 copies per minute so that both machines are simultaneously making copies. The answer is not 100 to this. What is the rate of copies made in the second equation? No. Think about it for a second while I answer the phone. Here's what we would write here. We would say we have already written or already made 80 copies. So we're starting already at 80. Then we're adding all of the copies we're making now at this rate. What was that rate you just told me? 180. But instead of just saying 180 times t, I need to take into account the amount of time that has already passed before this function took over. How much time has already passed? 1 minute. That is a vertical translation up for the amount of pages that have already been made, 80. And as a horizontal translation to the right, accounting for the 1 minute that has already been gone. Now our new rate takes over. Now what times is this function in charge? From what to what? From 1 to 3. Both of those are closed because exactly at 1 they both start, so I have a new function taking over, going all the way to 3 minutes when they both stop. Because these are our notes and that this would be really helpful for you on our test that's coming up next week or this week, let's write what this number was so we remember how we got it. What was that 84? Number of copies that what? The first minute. So number of copies at t equal to 1 that have already passed based on the other function. What was that number? How did we get it? I heard you say something, but I didn't hear what you said. Yeah, our combined rate. Both copy machines put together, our combined rate. And then why did I put t minus 1 instead of just t? That's how much time has already passed by, shifting it over to the right, time that has passed. Meaning that the entire parentheses stands for the amount of time working together. They're only working together for 2 minutes because the first minute's already gone, so we take it away. But that -1 right there is the time that has already passed. Questions, comments, concerns about piecewise? I know that feels like that was a half page of information about piecewise functions, but y'all have been picking it up pretty well, so I didn't feel like I needed to go into great detail here. No, we're okay?